Now let's look at example 3 of Hess's law. So go to the proper place on your handout, look at example number 3, take a look at the target equation that I'm trying to find the enthalpy change for, and then let us begin. I decided to go after reaction 1 because I need ethene, C2H2, to be a reactant, and so I'm going to flip reaction 1, which then is going to cause the enthalpy change to go from being positive to negative. So I've got one piece in position for my target. Next, I went to reaction 3, and I've decided that I'm going to flip it around. And I'm partly doing this because I need to get CO2 and water vapor as products. So this is what it looks like when I flip reaction 2 around. And not only do I get the CO2 and water in the correct place, I can kind of anticipate I need to get that C2H6, that ethane, to cancel out at some point. Nonetheless, at this point, by flipping reaction 3, I changed the sign on my enthalpy change from positive to a negative 849 kilojoules. Next, I go to reaction 2, and I am going to flip it around. Again, part of the job of a reaction is to get things lined up in the proper position so that I can get things to cancel out. And it's looking to me like I've got most of my components that I need in my target, but I know some things have got to cancel out. I've got to get things down to the right number. So I'm flipping it and I'm multiplying it by 2, and when I do that, it looks like this. Notice how I changed the coefficient of each term. I doubled them because that's what I needed to get the correct number to cancel out. Now, that means when I get the enthalpy change, I'm going to change the sign, but I'm also going to double the value. So that goes from being negative to positive, and then I doubled the 213.4, which gives me positive 427.4. Now I'm going to add these three equations together, and if I've kept my eye on the proper positioning and the proper numbers, things should cancel out and I should get to my target. Well, let's look at what does cancel out first. I notice that there are 2 hydrogens on each side, so they cancel out. Next, there's that ethane canceling out, which I mentioned a few moments ago. There was 1 molecule on both sides. They're now gone. Let's see what else cancels out. Water molecules. Now notice what I did here. I had 2 water molecules on the left side, but on the right side I had 3. So you notice I only x'd out the coefficient. So 3 obviously minus 2 gives me 1. And in that manner, the way I did it, you can see I still have 1 water molecule as a product, which is what I do need in my final answer. Next, I go after oxygens. I notice they're on opposite sides to each other. Be careful here, though. On the left side, I've got 7/2 oxygen molecules, and on the right side, I have 1. So obviously, 1 is really 2/2. So 7/2 minus 2/2 gives me 5/2. Notice how I just crossed out the numerator, changing it from a 7 to a 5. That looks like all that will cancel out. So on the reactant side, I have the C2H2 surviving and the 5/2 oxygens. And as products, I've got the CO2 and the water. Let's bring those down and see if my result matches up. There are my 2 reactants, which do match my target. And there are the two products also matching my target perfectly. So I did this correctly, so that means now, of course, all I've got to do is add up my three numbers, and they add up to a negative 705.1 kilojoules, and that is the enthalpy change for my target equation. So once again, Hess's law, combining equations in such a way that they match up and add up to the target equation.